Hello my good people, welcome back to my YouTube channel or the Big Structure Hub. This is a place where you learn, build and innovate. Today I want to solve the problem on the board, and this will be the last problem I will be solving under joist. So in my next session I will start designing compression members, and I want you to stay tuned for more design of timber on compression members. So this is the question on the board, and the question reads: check the adequacy of a 75 by 225 millimeter joist spaced at 500 millimeter center to center and 5 meters effective length given the following information. So dead load is equal to 1.25 kilonewton per meter square. Imposed load is equal to 1.5 kilonewton per meter square. Then the strength class is equal to SC4. The permissible deflection is equal to 0.03 times span. And then assume a medium term loading. Joist has a 75 millimeter notch on the underside, and then the length of bearing is 125 millimeter. So solution: determine the total loading. So total loading is equal to dead load 1.25 plus imposed load 1.5 kilonewton per meter square, like that. So the answer will be 1.25 plus 1.5, 2.75 kilonewton per meter square. So we need to reduce this to kilonewton per meter to obtain a uniform distributed load. So to do that, let's sketch this joist spaced at 500 millimeter center to center. So we know a joist is a horizontal member. So if I can sketch, so these are our joist members spaced at 500 millimeter center to center. So we'll convert this 500 millimeter center to center to meters. So it will be 0.5, 0.5, 0.5. So this is meters, meters, meters. And then to reduce this total loading from kilonewton per meter square, we'll take total loading is equal to 2.75 kilonewton per meter square times 0.5 meters. So meter 1, meter m. So we'll have 2.75 times 0.5. So this one will be 1.375 kilonewton per meter. This is our UDL. And then after this, we can now sketch a joist supported on two supports. So this is our UDL, which is 1.375 kilonewton per meter. This is support A, support B. And then the effective length is 5 meters. From this, we can calculate our maximum bending moment. So M max is equal to WL square over 8. So this one will be 1.375 times length 5 square over 8. So let's calculate it. So our answer is 4.3 kilonewton meter. Again, we can calculate our reaction. Or shear force. Which is V. So this one will be WL over 2. Our W is 1.375 times L, 5 over 2. So that is 3.4 kilonewton. So this is our V, and this is our maximum bending moment. So let me rub here to create space for more calculation. So the next thing is to calculate modification factors. Modification factors, which is K. So we'll start by K3. K3, you have been told assume a medium-term loading. If you check in the table, for a medium-term loading, K3 is 1.25. K3 is 1.25. Then we have another K, which is K7. So K7 is a K for a depth factor. And as you can see, our depth is 225. So we will have 300 over h raised to power 0.11. So for this case, our h, 300 over h, which is 225 over 0.11. Then you can punch your calculator and get the answer. So 300 over 225 raised power 0.11. So our K7 is 1.03. We proceed to K5 because we have been told a timber has a notch of 75 millimeter on the underside. So we have K5. So to calculate K5, you will need to draw the section of this timber showing the notched underside of 75 millimeter. So let's draw. So the original was 75 by 235. So this is Let me draw. So this is the original timber section. So we have 225 millimeter, and then 75 millimeter. But the timber is notched underside by 75 millimeter. So let's say this is the notch. So that is the notch. So we will remove this one like that. So this is our notch. Which is 75 millimeter. So the remaining of the portion from here to here will be 225 minus 75. So 225 minus 75. So that is 150. So the remaining portion is 150. So to obtain K5 for such a case, the formula is K5 is equal to HE over H. So our HE is this remaining portion after notching, which is 150. So this is 150 over H. H is this original height, which is 225. So again, I will repeat. HE is this remaining portion after you have notched this 75. So it will be 150. And then H is the original height, which is 225. Then you punch your calculator and obtain your K5. K5 is equal to 0.67. 0.67. So that is K5. So after that, we will proceed to grade stresses. So I will rub here again to create space for grade stresses. Before we can obtain our grade stresses, I have forgotten to calculate or to give the value of K8. So for K8, which is a load sharing factor, as you can see, this is the joists are spaced at 500 millimeter center to center, which means our K8 will be 1.1. For spacing less than 610, we will have our K8 as 1.1. So we can now proceed to grade stresses. So let me run. You will obtain the values of grade stresses from the table. So this is what will guide you. Strength class 4, SC4. And for me, I don't have that table for strength class. So what I have is as you can see on your screen, is what you call strength classes for service class 1 and 2. But in your exam, you will be provided with such a table. I will use what you are seeing on your screen to explain these grade stresses. So we will begin by bending parallel to grain. So the value is 7.5 Newton per millimeter square. So the table that will be provided will go for this strength class 4 and obtain this value. But for our case, I will compare strength class 4 with class 24. Check on your screen where my cursor is. So that class 24. So bending parallel to grain, as you can see where my cursor is. So that is 7.5. So as you can see, the value is there. Then we go to compression perpendicular to grain. So this is compression perpendicular to grain. The value is 1.9 Newton per millimeter square. In the table that will be provided, you'll go for this strength class 4 and go direct to compression perpendicular to grain and obtain 1.9 Newton per millimeter square. But for our case, I will go for the same class, which is 24, and go for compression perpendicular to grain. Compression perpendicular to grain. As you can see, we have two values. We have 2.4 and 1.9. So preferably, we'll use 1.9, which is the lowest value. So 1.9, as you can see. And then we go to shear parallel to grain. This is shear parallel to grain. Again, we will obtain this from the table of strength class 4 and write your value there. But for our case, I will again use class 24, the same class, to obtain shear parallel to grain. So shear parallel to grain, as you can see, where my cursor is pointing, is 0.71 Newton per millimeter square. I will proceed to E mean. So our E mean here is 10,800. 10,800 Newton per millimeter square. But for strength class 4, the mean is 9,900 Newton per millimeter square. So again, you'll obtain this from your table provided in your exam. So we go to permissible stresses. So the permissible stresses will have bending parallel to grain. So bending parallel to grain, our modification factor for bending parallel to grain, we have K3, K7, and K8. Remember K3, it modify all the grade stresses, and K7, it only modify bending parallel to grain. K8, it modifies again all the grade stresses. So bending parallel to grain, K3 times K7 times K8 times stress parallel to grain in bending. So our K3 was 1.25 times K7 1.03 times K8 1.1 times stress bending parallel to grain 7.5. So if you multiply, you will get 10.62 Newton per millimeter square. And then we proceed to shear parallel to grain. So shear parallel to grain will have our modification factor K3 times K5, again K5, it only modify shear parallel to grain, times K8 times stress parallel to grain in shear. So the modification factor for K3 is 1.25 times 0.67, which is K5, times 1.1, which is K8, times 0.71 stresses shear parallel to grain. So our answer will be 0.65 Newton per millimeter square. And then we proceed to compression perpendicular to grain. Again, we'll have K3 as a modification factor times K8, again as a modification factor, times stresses perpendicular to grain. So 1.25 times 1.1 times 1.9 will get 2.61 Newton per millimeter square. After that, we can now proceed to design. So let me rub here to create space for more calculation. So design consideration. I will begin by bending. So the formula for bending, we have to determine first Z, and we know that Z is equal to M over F, and our M was 4.3 kilonewton meter, and our F, that is permissible bending stress, is 10.62 Newton per millimeter square. So our Z is equal to 4.3 times 10 raised power 6. We are changing from kilonewton meter to meter to Newton meter. So this is Newton millimeter. So you are changing from kilonewton meter to Newton millimeter. So you multiply by 10 raised power 6 over F. F is 10.62 6, 2. So which imply Z is equal to, now you can punch your calculator and obtain the value of Z. The value of Z is equal to 404.9, no, 0.896 times 10 raised power 3. So Z is equal to 4 or 4.896 times 10 raised power 3 millimeter cubed. For us to check if our section is okay, we will again calculate our Z provided. So our Z provided will be, this is Z required, and Z provided is equal to BD square over 6. So our initial section was 75 by 225 millimeter. So this is our B and this is our D. So Z provided is equal to 75 times 225 square over 6. So this one will be, you punch your calculator, 75 times 225 square over 6. So the answer is 632.813 times 10 raised power 3 millimeter cubed. For our section to be okay, Z provided should be greater than Z required. So say therefore Z required is less than Z provided. Section okay in bending, like that. Then we proceed to shear parallel to grain. Let me create space for more calculation. So we proceed to shear You know that Q is equal to 1.5 V over BD. So V is our reaction or shear force we calculated earlier. V is equal to 3.44 kilonewton. We calculated this earlier. And then B is 75. And the D is equal to 225. So Q is equal to 1.5 times V 3.44. You convert again to Newton by multiplying with 1,000, 10 raised power 3 over 75 times 225. So let's obtain our answer. 0.31 Newton per millimeter square. We compare with permissible stress parallel to grain, which was 0.65. So 0.31 Newton per millimeter square is less than 0.65 Newton per millimeter square. Therefore, section okay in shear. After that, we proceed to bearing. So Q bearing is equal to V over Bx, whereby V is this 3.44 kilonewton and our B is still 75 millimeters, and X is our bearing distance. So our bearing length of bearing is 125. So this one will be 3.44 times 10 raised power 3. We are converting from kilonewton to newton over B, which is 75, times X, bearing length 125. Again, you punch your calculator and obtain your answer. The answer is 0.37. 0.37 Newton per millimeter square. Compare this with permissible compression perpendicular to grain. So 0.37 is less than 1.9 Newton per millimeter square. This is our permissible stresses perpendicular to grain in compression. So therefore, section okay in bearing. We proceed to deflection, the last design consideration. So this is 2.61 and not 1.9. 2.61. Sorry for the mistake. We proceed to deflection. So for deflection, we have been told the permissible deflection is 0.003 times span. So 0.003 times span. Our span is 5 meters, that is effective length. So if you multiply 0.003 0.03 times 5,000, you'll get 15 millimeter. And then after that, we go to induced deflection. So for induced deflection, this is our formula for singly supported beam: 5W L raised to power 4 over 384 EI plus 12W L square over 5 AE. So our W, we calculated our W, and it is 1.375 kilonewton per meter. We convert this to Newton per millimeter square. No, Newton per millimeter. So the value will remain the same, but the unit will change from kilonewton per meter to Newton per millimeter. And our length is 5 meters. So we convert it to millimeter, multiply it by 1,000, you will have 5,000 millimeter. Our E mean, this is E mean is equal to 9,900 Newton per millimeter square. We know that our I, the formula for I is BD cubed over 12. So our B is 75, this is 75, and our D is 225 over 12. So this is the answer for I. Area is length times width. This is the answer for area. So induced deflection will insert these values into this formula. So we have W as 1.375 times L this power 4, which is 5,000 times 5, this is 5, over 384. E is this one, and then I, this one, plus 12, this is 12. W is 1.375 Newton per millimeter square times length 5,000 square over 5 times area 16.88 times 10 raised to power 3. E is 9,900. So for this we have 19.9, 15.9, and for this 0.5. So our total induced deflection is 16.4 millimeter. So as you can see, our permissible deflection, which is 15, is less than induced deflection. So our section is not okay in deflection. For our section to be okay in deflection, our induced deflection should be less than permissible deflection. But for this case, it is the vice versa. So induced deflection is greater than permissible deflection. So for this case, you will redesign. You will choose another section if you are practicing structural engineering. But if you are a student, there is no need of going back and choosing another section. So what you need to do, you'll just leave your answer at this point and you'll score all your marks. So that marks the end of this question. To wind up joist design, this is a point to note. Timber section occasionally have to be checked for lateral buckling, which is compared to a maximum depth to breadth ratio as given in table 19 of BS 5268. So occasionally it means from time to time. So when you have installed this timber joist, you need to check for lateral buckling and compare the value to these values given in the table 19 of BS 5268. So that is all about the design of joist. So in my next session, I will start designing compression members. And this is the question to practice. A timber joist 100 millimeter by 250 millimeter of effective span 4 meters at 500 millimeter center to center bears on 200 millimeter wall. Using the data given, determine the permissible load per unit area which can safely applied on the wall given that dead load is equal to 1 kilonewton per meter square. So strength class is equal to SC5, permissible deflection is equal to 0.03 times span, and assume a medium term loading. So practice the question, and if there will be any difficulty in the process of calculating the permissible load area, you can reach me in comment section and I will help you. So in my next session, I will start design of compression members. So stay tuned. And for those who have not subscribed to my channel, please, I request you to subscribe so that you may be the first person to be notified when I upload a video. So thank you for your time, and we meet again in my next session.